So, collection of organic redox reactions taken from the various A-level papers. Not a whole heck of a lot of variation between these. I think you'll notice about 3 themes developing. Anyway, stress type of reaction occurs between ethine and hydrogen. So there's ethine, reacts with hydrogen to make an alkene, then more hydrogen to make an alkane. One often calls this hydrogenation. It is an example, of course, of an addition reaction, but it's also a reduction because we are adding hydrogen atoms to those carbons. State the reagent used to produce phenyl methanol from benzaldehyde. There's benzaldehyde. There is phenyl methanol. You can see it's a reduction. We're going from an aldehyde to a primary alcohol. We are adding hydrogen atoms, all kinds of different ways you can recognize this as being a reduction. And of course, to do a reduction of an aldehyde, you can use either of the chemical reagents, either the sodium borohydride in aqueous solution or the lithium aluminium hydride in ether. Of course, remember, this is a much stronger reducing agent than this one. Either of these will work when you want to reduce a carbonyl compound like an aldehyde or a ketone. However, if you want to reduce the carboxylic acid, which is of course the one before the aldehyde in this little sequence of acid, aldehyde, and primary alcohol, then you have to use the lithium aluminium hydride, and we'll see that several times in future questions. So on the last slide, I mentioned the reduction sequence, acid going to aldehyde, going to primary alcohol. Now we're going to see the reverse of that, oxidizing primary alcohol through the aldehyde that isn't mentioned to the carboxylic acid. You can tell that it's an oxidation because you've increased the number of oxygen atoms from 1 to 2. You've decreased the number of hydrogen atoms from 3 shown to just the 1 here. So very definitively an oxidation. Now this is an oxidation that needs very little subtlety at all. So we can use any of the standard reagents that you know. We can use the acidified chromium 6, which is H+ for the acid, and either chromate or dichromate, or we can use the acidified permanganate. Both of these involve color changes. The chromate is yellow in solution, dichromate is orange in solution, and both of those in acidic solution will get reduced down to the green chromium 3. Of course, remember, if you're oxidizing here, this needs to be reduced. Then, of course, permanganate, glorious purple color, and ultimately, when it's all used up, goes colorless as you go from manganese 7 to manganese 2. You're going to see this little section here quite often as we go through nice oxidizing agents. Dimethylbenzene 1,2-dicarboxylate, DMP. This can be made by oxidizing 1,2-dimethylbenzene, followed by acidification resulting product, and then esterification. So the oxidation is what we're looking at here. So we got 1,2-dimethylbenzene, which we will then oxidize to give us the dicarboxylic acid. You can see where those dicarboxylic acids have then been esterified. So how do we oxidize from this methyl group to the acid group? Acidic conditions, and then again either the chromium reagents or the permanganate reagents that we listed below, or what they're really looking for here is the alternative to do it in basic conditions. So basic, OH-, with the permanganate, and you can tell this is what they're looking for because then they say they acidify the resulting product. Okay, and when you use these basic conditions, you don't make the carboxylic acid, you make its conjugate base, which you then need to acidify. And we'll hit this once or twice in the rest of this worksheet as well. Oh, and here it is. Why is it necessary to acidify the product? Because the basic conditions make the conjugate base, so that's COO- instead of COOH, which you then need to acidify to get the acid itself. Acid was known to be one of the following. Draw the structural formula of the alcohol that can be oxidized to make acid 2. Well, here's acid 2, and you see it's got 2 acid groups there, which means we have to have 2 primary alcohol groups in it as well. It's 1, 2, 3, 4 carbons, so it's just going to be 4 carbon butane, 1,4-diol. Methanol, liquid room temperature, molar enthalpy of combustion can be found directly, gee whiz. Write the equation corresponding to the standard enthalpy change of combustion of methanol. Well, There's our methanol there. When we combust, we're reacting with oxygen, and the products are the oxides, so carbon dioxide and dihydrogen monoxide, otherwise known as water. Why is this in this section on redox equations? Well, because if we look at the oxidation numbers, or the oxidation state of carbon, it's -2 here, because the 4 oxygens plus 4, the oxygen -2. So to make it neutral, the carbon has to be -2. Then going over to carbon dioxide, oxygen -2, 2 of those -4, so the carbon must be +4. So the carbon gets oxidized. Now, of course, anytime you react something with oxygen, you can say it's an oxidation. The oxygen atoms go from 0 to -2, so they are, of course, reduced. So this is an oxidation reaction as far as the methanol is concerned. Got to balance it. Got 4 hydrogens, so we need 2 waters. Now we have 2 plus 2 oxygens. We've already got 1 there, so we need 3 more oxygens from the O2. So ordinarily, you'd multiply everything through by 2, but in this case, it wanted the standard enthalpy change, which means you can't multiply it by 2. You have to have 1 mole of methanol, which means we need 3/2 of the O2.